Hi again. Today we're going to talk about the internal energy of a gas. What I mean by the internal energy is the energy of the gas taken as a whole by adding up the individual energies of the molecules of the gas. Kind of think of it this way. Gas particles are bouncing off of each other rapidly. Now this is kind of in slow motion here, the bouncing, and this would be two different gases, I guess. We have some blue molecules and some red molecules, and by the way, molecules don't really have colors. But they would really be moving at hundreds to thousands of miles per hour. They are very, very quick, and those collisions would be happening extremely quickly. It's the bouncing off of the walls of the container that gives the gas the pressure that it has. The energy that the gas molecules have is related to that pressure, and you'll see how that is soon enough. Turns out that the internal energy of a gas is directly related to the amount of gas, of course, more gas means more molecules, and the temperature of the gas. As you heat the gas up, the molecules move faster, and as you all know, the formula for energy is, or kinetic energy, I should be more specific there, for the kinetic energy of the particles is 1/2 mv squared, where m is the mass of the particle and v is the speed of the particle. And so the faster it moves, the more energy that it has, and the temperature is related to that energy as well. The formula for the temperature relationship is this. U stands for the total internal energy of the gas. That's the sum of all of the particles' energies put together. And it turns out it's equal to 3/2 times N, which is the number of moles of the gas. And if you don't remember what a mole is, it's an Avogadro's number, 6.023 times 10 to the 23rd power, which is a lot, by the way. Particles, that's a mole. So it's the number of moles times what's called the gas constant, times the temperature, which don't forget is going to have to be measured in Kelvin. That is a scale measuring from absolute zero. And so the warmer the gas is, the more energy it has, because the faster the particles are going to be moving. Makes pretty good common sense. Now this formula has the 3/2 factor in it because of the fact that if you, say, have a container of gas, I'll see if I can draw one here a little bit. Here, we'll make it a box. Okay. That the particles can be moving in any of three directions. Well, technically they can be moving in any direction, but that direction of motion can be broken down into components in three directions. They could be moving across, or they could be moving back and forth, or they could be, that is front to back, or they could be moving up and down. And that's where that 3 comes from in the 3/2. The 1/2 comes from this 1/2 right here. The rest of it I'll leave to someone else's video to explain where the formula comes from. But understand that it just works for molecules where their only kind of motion is translational. That means back and forth. If you have a diatomic molecule like oxygen, so you have 2 oxygen atoms bonded together, then it can also rotate in this direction, for example, or it could rotate around in and out of the page horizontally. And so that adds what are called degrees of freedom, and that would increase the potential, or the amount of internal energy. So it's 3/2 nRT. Those of you who remember your ideal gas law, and we are talking about a monatomic gas, so it's pretty much an ideal gas like helium or neon. Remember that PV equals nRT, the ideal gas law. And so for this monatomic gas, we could also write that the internal energy is equal to 3/2 times the pressure of the gas times the volume of the gas. And if you want that energy to be measured in joules, then the pressure would have to be in pascals and the volume would have to be in meters cubed. Okay, but the key thing I want you to remember, internal energy of a gas relates to the amount of gas and the absolute temperature of the gas. Okay, and so we'll move from there. The first law of thermodynamics tells us that there are only 2 ways to increase the internal energy of a gas. The total change in the internal energy of a gas is equal to the heat added plus the work done on the gas. We saw in the last lesson that if you do work on a gas, you can cause the molecules to speed up. Say by pushing down on a piston, the molecules that bump into that piston will come off of it at a higher speed than they would if the piston were not moving. Okay, so that's the work added. And of course, if you add heat, that means you're directly putting it in contact with something that's warmer, so heat is just transferring into the gas. So those are the two ways to change the internal energy of a gas. The formula is the change in internal energy. Notice the delta right there, that matters. This is not the internal energy, this is the change in internal energy, is equal to the heat added, that's Q, plus the work done on the gas, which is what we discussed last time. So for a gas, since the internal energy depends on the temperature, if we have an isothermal process, meaning the temperature is not changing, the change in temperature is 0, then that means the change in internal energy is 0. Not the internal energy, the change. So that means the internal energy is constant if the temperature is constant. They are absolutely dependent on each other. Thus, since, and I'll remind you of the formula we had on the other page, since the change in internal energy is equal to Q plus W, if this is equal to 0, then the heat added to the gas is equal to the opposite of the work done on the gas, or in other words, it's equal to the work done by the gas. Okay? So if the system is isolated, meaning it's not in contact with any outside systems, the change in internal energy is 0. The heat added is 0 because, like I said, it's not in contact with anything. So therefore, it cannot do any work and no work can be done on it. Okay, that's what happens when you have an isolated system. Nothing. For a cyclic process, now this is just a definition, I'm not telling you anything interesting about it. The gas ends in its original state. That is, if it's gone through a process of pressure, volume, and temperature changes, in a cyclic process, it eventually comes back around in either a simple fashion or a circuitous fashion to the original pressure, volume, and temperature. So that means, since it has the same original temperature, that the change in internal energy is 0, and so once again, any heat added is the amount of work done by the gas, or is the opposite of the work done on the gas. Let me show you what I mean with the graph here. This is an example of a cyclic process. Let's say that we start here. That's the state it's originally in, that pressure and that volume. Okay? Along the bottom here, the gas is expanding. The volume's increasing, right? Going from here over to here. Since the volume is increasing, that means the work is being done by the gas. So the work done on the gas is negative. It's less than 0. Over here on the right side, as we move up here, the volume's not changing, so therefore no work is done, as we learned in our previous lesson. Up here on the top, the work done on the gas is positive because the gas is having its volume decrease, so somebody's pushing on that piston, somebody's making the volume smaller. So work is being done on the gas, the work done on the gas is positive, and once again over here on this side, the work is 0. So therefore, the net work done is the area enclosed. What do I mean by that? Well, if we look right here, the work done on this branch down here at the bottom would be this area. Okay? Now let me change colors. As we're coming across this top branch, the work done is all of this area here. But this area is positive, whereas this area down here was negative. And so we'd have to subtract the big area, the big rectangle, minus the little rectangle. What does that leave behind? The area that's enclosed by the PV graph. Okay, so the net work, maybe I'll put the word net in there. And I put the absolute value sign because depending on which way the cycle goes, you could end up with a net work that's either positive or negative. In this case, it would be positive work done on the gas, but if it was in the reverse direction, it'd be positive work by the gas or negative work on the gas. It's just the area enclosed by the cycle as drawn on the PV graph. Pretty straightforward. So let's suppose we have a cylinder here. The surface, or not the surface area, the area of the lid, that is of the piston, we'll say is 0.10 meters squared. The pressure of the gas is 8,000 pascals. And we're going to have the volume change by having the gas expand like that. Okay, so delta Y is positive 4 centimeters. So that means work is being done by the gas, or negative work is being done on the gas. Furthermore, we're going to add some heat to the system by putting a candle underneath it there. So we're going to add heat. Now, there may be heat escaping out of the side walls because it may not be perfectly insulated. So there might be some heat heading out that way also. We'll call that Q loss, something like that. So let's take a look at some numbers. Let's suppose that 50 joules of heat enters because of the candle, and 8 joules of heat escapes as a result of losses of heat through the side. Our question is to find the change in the internal energy of the gas. Seems really complicated, doesn't it? Well, not so much. You see, all we have to do is use the first law of thermodynamics. It says that the change in internal energy, and that is what the question is asking for, is equal to the heat added plus the work done on the gas. But don't we have formulas for that? Absolutely. The heat added is 50 joules minus 8 joules, because there was some heat lost to the environment, plus the work done is negative P delta V if we're at constant pressure, which is what this problem says. And so this is going to be 42 minus the pressure is 8,000 times the change in volume. Well, how do you find the volume of a cylinder? Well, that's pretty straightforward. The volume is the area of the base times the height. And so the area of the base is 0.1 times the height. That's 4 centimeters. That's 4 1/100ths of a meter. Remember, we have to do this in terms of meters. And so if we continue doing our math correctly, we have 42 minus, well, let's see, 8,000 times 0.1 is 800. 1 100th of 800 is 8 times 4 is 32. And so the answer is positive 10 joules. So that's the total heat gained by the gas, the total internal energy change of the gas due to adding heat, which increased it by 50 joules, and heat escaping out of the sides, which decreased the energy by 8 joules, and the work done by the gas. It's just like you. When you do work, you lose energy. Same thing for a gas. The gas did the work of pushing outward on the cylinder, pushing upward on the lid, and so as a result, it lost some heat right here, 32 joules, for a total of 10 joules. And that's it. That's how you use the first law of thermodynamics, at least in a very simple example. So I hope that makes sense to you, and I'll see you next time.